So again, welcome everyone to this user preparation webinar on the next generation spectral images, FCI and MetImage, organized by EUMETSAT. I am Stefan Brzezinski, the MTG user preparation project manager, and I welcome more than 185 participants from all around the world who have registered today. EUMETSAT is planning to operate the FCI, the Flexible Combined Imager, on the next generation MTG satellites as of 2023, with the launch of the first planned for end of 2022. The MetImage is planned to be launched and operated on the METOP second generation A satellite, the first to be launched in 2024. We organized this webinar as the fourth in a series of user preparation webinars on the observation missions on the next generation MTG and EPSSG programs. It feels a real privilege to be here because we are building on tremendous experience that has been built up in the European and beyond communities by using Severi for more than 17 years, and by using AVHR, MODIS and VIIRS on the polar orbit for many, many years. So the big slogans here are continuity for members and users with enhancements in resolution, as we will see, but also we have a lot of innovation by adding new channels and serving new applications. We are benefiting from the experience gained by users of the GOES ABI instrument data and the Japanese Himawari instrument data, which have been operating since 2017 and 2015, respectively. So with FCI, EUMETSAT is closing the geostationary ring of next generation images. Today, we focus on the FCI, the Flexible Combined Imager on MTG, and level 1 data generation. Tomorrow, we focus on MetImage and level 1 data generation. We'll have short demonstrations of visualizing some of the data, and we give perspectives on the applications that we will support with these new missions. On Thursday, the 10th of June, we'll have an overview of the geophysical products that will be derived from the new images, with a focus on those that are produced by EUMETSAT at its central facility. There are many, many other products being produced by users and within the EUMETSAT satellite application facilities, which we will mention but not provide any further details. We'll plan to organize other webinars on the satellite application facility plans. So it feels like standing on the shoulders of giants here. We try to give it a comprehensive overview. We try to do justice to the tremendous experience that has been collected in the community. I'm sure we will do our best, but we cannot do justice to all the applications and achievements, but we'll do our best today and in the next couple of days. So with this webinar, please ask your questions using the Slido tool, www.slido.com, and enter the event code #NG-images, and we'll try to answer your questions during this event or afterwards in writing, and we'll make all the questions and answers available to you. We'll also record this event and we'll make the recordings available and the presentations. So please use the Zoom chat only for if you have any technical questions in hearing or seeing us. Keep muted and your videos off during the event, please, to save bandwidth. And with this, I'd like to close and hand over to the first speaker, who is my colleague Munir Lekwara from EUMETSAT. Munir, you have the floor.
Good afternoon, everybody. Thank you, Stefan. Can you hear me well?
Yes, good.
Okay, thank you. So you should now see my screen, I believe, in presentation mode.
Yes, it's all good.
Okay, very good, thanks. First of all, I'm happy to present the FCI instrument to everybody today. I'd like to acknowledge also my my co-authors, this 4 gentlemen here, from whom I stolen a few slides and materials. So we have also Gary Fowler and Stefan Wojinski from EUMETSAT, as well as Doni Aminou and Yannick Durand, who were for Yannick and is for Doni responsible for the procurement of the instrument with industry. A few words about MTG first before diving into the FCI payload. We'll talk, of course, about MTGI, the imaging mission, which with the FCI will offer a full disk imagery every 10 minutes with 16 bands. We'll come back to that. But also with the possibility to do fast imagery over Europe every 2.5 minutes. MTGI will also host a new payload for Europe, the lightning imager for, of course, obviously lightning detection. Start of the operations will be in 2023, and operational exploitation will go on for 20 years. A few words about the transition from MSG to MTG, because I think this is important for the users. As we launch MTGI, let me use a laser pointer. Okay, as we launch MTGI1 in end of 2022, we'll of course go through the commissioning and put it in 0° longitude position. But 1 year after launch, MTGI1 will become operational, and we will enter what we call the initial operational capability, IOC. The second table here is presenting the different operational capability services that we have planned. So as I said, the IOC will start in 2023 or early 2024. And in this service, the full disk will be offered by FCI. But we'll have also, of course, a backup with MET10, also close to 0° longitude. The RSS service will be delivered by MET11. 1 year later, towards the end of 2024, we'll enter the partial operational capability, where MTG and MSG won't change, but we'll have MTGS launched. 1 year later, we will essentially switch off Severi service from over Europe. So users will have to be ready as of end 2025 to use, of course, MTGI data for the full disk and MTGI2 over RSS. Yeah, this is essentially all our users will have to be ready for switching off Severi over Europe. But of course, we're hoping that everybody will start using MTG data as early as possible, because of course, as you will see, it will bring a lot of enhancements. Okay, a few words about the FCI missions. Actually, we'll talk about the FCI for the rest of the presentation. So the FCI will provide the continuity of the service from Severi for both the full disk scanning services and the rapid scanning service. It will offer additional channels and improve spatial, temporal, and radiometric performances as compared with MSG satellites. The requirements for these instruments are driven by nowcasting and very short-term weather forecasting, plus regional and global numerical weather prediction. Over here, you can see, okay, this is a Severi image, a true color imagery. We have here a various RGB, and these are the sort of display that will be enabled also by the FCI. Of course, we'll have also level 2 products, which you will hear from on Thursday, such as OCA or the AMV, so the atmospheric motion vectors, the winds. Okay, for the development of the FCI, this has been handled, of course, on behalf of EUMETSAT, but by the European Space Agency via a consortium which was led by Thales Alenia Space France, actually in Cannes. The first model of the FCI, the proto-flight model, which we call the PFM, is assembled and being tested currently in Cannes in the optical vac pre-launch test campaign. This campaign is almost completed, and once that's done in July this year, the instrument will be integrated on MTG I1, and it will then undergo further testing, but fixed on the platform, on the full satellite, basically. So we call it the thermal vac testing. This will occur between October and December 21. We should mention also, of course, the operational processors, both at level 1 and level 2, which are really complex programs. And those are under direct responsibility of EUMETSAT. The level 1 is being developed by Thales France, and the level 2 by Thales Services. Let's talk a bit about the FCI bands. Here we have a nice comparison by Ivan Smiljanek between the ABI on GOSAR series, the FCI on MTG, and the AHI on Himawari. Because as you see, the FCI will slide in between two excellent instruments, ABI and AHI, to offer similar capabilities and complete the geo ring of geostationary imagery observations from new generation instruments. The FCI bands are pretty similar to those of ABI and AHI, with subtle differences, which we can highlight here. We have what we call a green band, the 0.5 or 51 micrometer band, which is on AHI but not on ABI. We have also a V-zone, what we call the V-zone 9 band for water vapor, in particular in close to the surface. This would be a new band in geostationary. We also have a 1.3 band, which is present on ABI for the cirrus detection. Then we have the same near band, so the 1.6 and the 2.2 for cloud phase and particle size. And in the infrared, we have, of course, the fire band 3.8, and we have only two water vapor band, 6.3 and 7.3. We don't have the 6.9. Then we have the cloud phase, ozone, and the clean band 10.5. We do not have a band at 11 micrometer. We then jump to the 12.3 and the dirty band, and the 13.3 for CO2 band. A word about the spatial resolution, so what we call the spatial sampling distance. It's also rather comparable with ABI and AHI. We have 1 kilometer for the V's and the near, and 2 kilometers for the IR. Of course, that's at nadir. But in addition, we have 4 channels with twice as small resolution here. So we have the VISO 6 is provided at 500 meter, like for the ABI. We have also the 2.2 provided at 500 meter, and you can see here this little square represents the resolution on ground compared to the map behind, but at least to the other channels. And the other 2 high resolution channels are the 3.8 and the 10.5, which are provided those at 1 kilometer. It's worth to compare with Severi. I've added those colors here, so you can see in green are the heritage band from Severi. So a lot of the bands, of course, are continuation of the Severi band, even though there are some subtle differences again. And you can see the new bands for the European coverage are those 5 bands here in dark blue. The resolution of Severi is 3 kilometers. So as you can see, this is a huge improvement for the European users. I've plotted here the spectral response functions for the FCI and the Severi bands. The FCI bands are in the bold lines, and the Severi are the dashed lines. So you can see, of course, we have new channels which are not present on Severi, but even for the heritage channels, we have subtle differences in the spectral definition. Mostly, we have narrowed the bands. You can see it in particular for the 1.6 band. Also for the 3.8 band, we have removed absorption bands there from CO2. And another important difference between FCI and Severi are the differences for the 10.5 and the 12.3, which have been narrowed and shifted apart from each other. So users have to account for this in their product, obviously. To give you a little bit of a feeling about the improvement in resolution coming from Severi and going to FCI, this is a, okay, let's say this is a grid at 3 kilometers resolution from MSG Severi. Now for the FCI infrared bands at normal resolution, we have a grid of 2 kilometers. This is already quite an improvement. But for the IR high resolution and the VIS-NIR normal resolution, we are a grid at 1 kilometer resolution. And then of course we go down to 500 meters. So that's a lot more data that people will have to deal with, but of course a lot more content in the data. We rectify all these grids on a common reference, so it's easy to use the bands in combination with each other. The impact on the image, so to get a bit more feeling again about what we should expect to see, we have here a natural color RGB from MSG over Sicily in the Mediterranean. And this is what Daniel Rosenfeld expected that we would see with the FCI. So of course, it's using this image at 1 kilometer, but you can see that once you go from 3 kilometers to 1 kilometer, and also using the real blue and real green band, suddenly we can retrieve much more details. We can see vegetation, we can see, of course, ashes, we can see small clouds, and so on. In terms of temporal resolution, because we also get our imagery, our images more frequently. For MSG, we are getting from Severi the full disk every 15 minutes. So time t plus 15 minutes plus 30 plus 45. For the full disk of FCI, it would be reduced to 10 minutes. So of course, it would be much more frequent. And the RSS service from MSG is a third of the disk every 5 minutes. Whereas for FCI, it will be every 2.5 minutes. So you can see here much denser data. This is a summary of what we will get from the two modes of the FCI. We will get we can set it up either in a full disk mode where we acquire the full disk in 10 minutes, or in RSS mode where we acquire a quarter of the disk, northern quarter of the disk, every 2.5 minutes. What you see here are the source, the acquisition source, but in the product, they are not present anymore. The image is rectified. The summary of the benefits from the FCI. Vesa later today, I think it's the last presentation, will elaborate each of those points. I think it's good to have an overview at this point. For the new channels, the first two channels, VISO 4 and VISO 5, those will support true color images, but also will improve aerosol retrievals, in particular over land. The VISO 9 channel will provide total column principal water over land. And it's quite important, of course, for a convection, in particular, to know the content of water close to the surface. The new near 1.3 micrometer channel will improve the detection of very thin cirrus clouds, which we don't see currently with Severi. We do detect cirrus clouds with infrared, but not the very thin ones. And once when those clouds are not detected, then the small errors are introduced in all the clear sky products. The 2.2 micrometer channel will provide a better retrieval of cloud microphysics. The higher spatial resolution, 1 kilometer and 2 kilometers for the 3.8 channel, will improve the fire detection. So we'll be able to detect smaller fires. And we also have an extended dynamic range where we shouldn't be saturating as much as we do on Severi, so which will improve the quality of the products. We'll be able to retrieve the FRP much better. So generally, we'll improve the convection detection through a shorter repeat cycle and better spatial resolution. Let's go into the FCI optical design and detection system. You can see here a schematics of the FCI instrument. The light comes through this path here. So there's actually also a baffle which is mounted on top. You may have seen on the photos. So the light comes in through the what we call the scanning mirror. We call it also M0, and then it enters a three mirrors anastigmatic off-axis telescope. So sorry for the jargon. It bounces off first the second mirror M1 and third mirror, which is called M2. We have here a refocusing mechanism, which will maintain the proper focus in orbit. And we have another mirror, and over there we are entering the spectral separation assembly, which basically splits the light into the different focal planes. So the visible photons are sent onto the visible focal plane over here, whereas the infrared and near are split over 4 focal planes, where you can see here these little lines here are the different channels. And the near and IR detectors sit here in the cryostat at very, very cold temperature to ensure, of course, excellent radiometric performances. The visible detectors are CMOS detectors, whereas the IR are NCT. For all the channels, we have the same shape of detectors, and those are of the pixels, and we call them rhombus pixel. You can see those here. This is the direction for the east-west along track, and this is the north-south swath. Of course, this is just a horizontal slice of the detector. We have actually the column goes on really, really far down. And you have 4 different colors corresponding to 4 different redundant columns. So we can activate the pixels from one. We have 3 redundant pixels in case a problem occurs. So this yellow column here would be the nominal column. And if, for instance, so this is the first pixel, second pixel, third pixel, fourth pixel, fifth pixel, 6th pixel, and then if the 7th pixel has a problem, then we can configure and activate a pixel from another column here. For in that case, this one, and it continues and so on. Okay, I thought it would be nice for you to see the real telescope. Of course, this is just part of the FCI. We can see here, this is the flight model of the telescope optics during the alignment. We don't have here the scanning mirror mounted yet, but you can see here the second mirror, and I think the third mirror is somewhere here, and the fourth. It's important for the users to understand the difference of this data collection as compared to Severi. So I'll come back to Severi for a minute. As you know, Severi has a continuous east to west scan. So the whole platform is spinning, and it's scanning the Earth and then the deep space around the satellite with 3 pixels, which corresponds to a swath width of 9 kilometers. And then we have a little north-south movement, and we scan 3 more lines of pixels, and we continue like this. We scan the whole Earth. So the maximum time, I mean, of course, the spinning is extremely fast. So the maximum time difference between 2 lines are the difference between 2 swaths, and that's 0.6 seconds. So nothing has really moved there on Earth. For the FCI, we have what we call a 3-axis stabilized platform. So we are staring at the Earth for the whole duration of the mission, and we have the scanning mirror, which is scanning over the Earth here and acquiring larger swaths this time. We have swaths of 180 kilometers as opposed to 9 kilometers, and this is the movement here. I should start this. So we have here a typical scanning for a full disk, where you can see the swaths being acquired, scanning from east to west and west to east, and then with a little north-south movement. We acquire a bit of deep space, and then we come back on the Earth. So we spend most of our time looking at the Earth as opposed to Severi. What happens around the equator, for instance, is that it takes 10 seconds for a source to be acquired and another 10 seconds to come back. So we may have about 20 seconds difference on both sides of the, from one pixel to the next on the L1C image. Then we have what we call a yaw flip. I'll talk to it in a second, where the whole platform gets flipped. So this will reverse the detectors. So the actual pixel element, which is either at the north end of the source or the south end of the source, this will change twice a year, but the scanning pattern will remain the same. So this is the yaw flip. Twice a year at the equinox, we have to do a yaw flip. Let me see if I can start the animation. So as we look at the Earth, every day, every night around midnight, the sun comes close to the Earth, and around the equinox, the sun is around the equator when this happens. We try to keep the radiator, which are on one side of the platform here, shielded from the sun, such that the heat from the detectors, the infrared detectors, can radiate and escape the platform. So when the sun arrives at on the equator, then what we do, we flip the platform here, such that we put the radiators on the north side here, and the sun will continue to travel here and looking at the bottom of the platform here, and still not seeing the radiators. So we want to keep those away from the sun. When this happens, so twice a year, there will be a close to 4.5 hours outage, and that's the time for the platform to rotate, to stabilize, and for the navigation to also converge. Let's talk now about the calibration strategy for the FCI. We have what within the instrument an accessible intermediate image, which is behind the field stop. Again, really within the telescope. This wheel, when it's open, we call it a free beam. The photons coming from space and the Earth go through here and be acquired. But we can rotate this in the field of view, and we can then put in the field of view either a metallic neutral density, which is a very high density filter to look at the sun and calibrate with the sun, or we can rotate a little black body to calibrate the infrared. We can also put a shutter in to protect the instrument in case of problem. So this is the black body here. I think it's being fitted here. So it's very small. It's within the instruments, and it's of course a very important piece of subsystem, because the performance of the radiometry depends on it. For the infrared, you can see the Earth and the source. As we acquire the source, of course, we have the useful pixel on the Earth, but then we go into a bit of deep space, and there we acquire the offset of the instruments. So at each source, we take the offset to correct the actual source on the next one. And when we have finished acquiring our disk, we then what we call a retrace, where the scan goes into deep space, and then we come back here ready for the next repeat cycle. And during that time, we have a black body acquisition. So this wheel is rotating in the field of view, and we have we measure the signal here from the black body and at the temperature, which is also very well measured, so we can calibrate on. For the vis and the near channel, we use the sun to calibrate. So here you can see two MND. So this is the mirror neutral density. As I said, it's a high density filter. It brings the dynamic of the sun into a much lower level that doesn't saturate the instrument. But of course, the sun is a well-known source. So we put this MND on, and we acquire what we call a lag 4. So it's basically it's RSS. And when we scan over the sun, then we can we use a signal to calibrate the vis and the near. We do this, I believe, twice a year also. And when we do this, and we have a blind lag here. So because of course, when you look at the Earth, then it's just completely dark. We have no useful data. Let's talk about the processing. So level 0 to 1 processing. We get the data from the satellites. We call the raw data. We first calibrate it radiometrically. We apply a nonlinearity correction algorithm, which is on functions that are characterized on ground on the detectors. We calculate and apply the offset and the gain from the MND and the black body. We have complicated correction algorithms for stray light, both in field and out of field. So the stray light from in field is a stray light from the Earth itself. We call it also the Earth stray light. And the out of field is when the sun is close to the Earth. We have the halo around the sun, like we have for Severi, and we have a correction for that. We also have spatial frequencies adjustment, so we improve the focus on some of the channels. We merge the fire channels because, in fact, on the instrument at level 0, we have 2 different channels, one with a low gain, one with a high gain, so that we can extend the dynamics of the fire channels. But the users are getting only one channel. We have to merge those 2 into one. We also have a step which is called high resolution to normal resolution resampling, where we take the high resolution channels, 4 of those, and we generate normal resolution channels from them, where we subsample them basically, and maintaining the focus. Extremely important and complex step is the geolocation, because we want this to be extremely accurate, and we are also scanning from really far with a big telescope. So what we do is we extract observables. So for the FCI, we use landmarks, so sort of coastlines. We also look at stars. And we have a system state estimation process, which is pretty much a Kalman filter where we estimate all the biases within the instrument and the platform. Those biases are then calculated every 10 minutes, and they are applied into a line of sight model combined with AOCS data. So that those are the star trackers and the gyro, which provides the information about the platform attitude. We have also the scan readings, so we know at every millisecond where the scan has been pointing, and ranging data, which provides information about the satellite orbit. And with this line of sight, we are able to calculate for each of the pixels on the swath geographical coordinates, so a lat and a long. We have a quality reporting stage also. And at the end of this process, we have what we call a level 1B swath. So we have an image, which is the east to west swath with the radiances calibrated, and also with the lat long associated to each of those pixels. This is not what the users are getting. What the users are getting are the level 1C products. They are rectified on a fixed grid. So all these swaths are combined and rectified onto a fixed level 1C grid. And that's what users are getting. The same as for Severi. About the performances, you can see the specifications of the requirement in the end user's requirement document, which provided here a link for. The actual performances are currently being measured in the optical vac test at instrument level. They will be communicated to users in autumn this year, but we are pretty pleased with the general status of the performances, of course. Just to give you a feeling about what the sort of tests that are being held in ground. This is here for the subsystem of the spectral separation assembly together with the detectors. They are over here, and this is here optical ground support equipment called the jigs, which provides a calibrated source here and allows to test basically the detectors. This is a stray light measurement facility where we have then put the FCI instrument on top here. It's not there yet. And over there we have also a very bright target, which allows to characterize the what we call the BRDF, so the optical properties of the telescope mirrors to calibrate the stray light model that we use to correct the data. I will expand a bit in the radiometric requirement because it's quite important. So you have here all the channels of the FCI with their resolution. Some of them have high resolution and normal resolution, and sometimes you have different specifications for those two products. It's important to understand the concept of reference signal because it is used for the requirement. So the reference signal for the Wiesner, it's a very, very dark signal, is 1% of reflectance. Whereas for the infrared, the reference signal is a temperature which varies as a function of the channels here between 200K and 250. We have first the radiometric noise, which I think you're familiar with. For the Wiesner, we quantify this noise as a signal to noise ratio. So the higher this ratio, the better our data is. And you can see those are the requirements for all the channels between 30, 40, I mean up to 40, and for the high resolution channels, for instance, down to 12. The noise for the infrared channels is quantified with a noise equivalent delta temperature. So it's actually noise in Kelvin. And those are, you want your system to have as low NEDT as possible. We have here down to 0.1 Kelvin. And for the higher resolution, we have we allow a higher noise. And we have a special case here for the extended range of the IR 3.8, so the fire, we'll say the warm range, we have up to 1 Kelvin because we go to very high temperatures. This noise here, it's important to also to understand that it's we have a scaling applied to our requirements. So let's talk first about the Viz near. This is an example here. This is the near 1.3 channel. You can see, for instance, the 1.3 requires SNR 40. Okay, at the reference signal, which is a very small reflectance here. So it's this point here. This is the requirement. But for higher reflectances, we expect the performance to be better, so to have even a better SNR, and this is the requirement then. And you can see here plotted both the worst case performance in green and the typical performance in magenta here. So here we have a very small non-compliance for the very dark scenes. We're just about touching the requirement line, but you can see the performance is pretty good and much better than expected. For the 10.5. The high resolution. So let's look again. We talk about so the 1 kilometer channel. We are at 300 Kelvin. We want to be below 0.2 Kelvin of noise, and this is this point here. So we have also in the URD you will find a scaling function which is applied. So here you want to be below the curve here to have a low noise in Kelvin. So we also here compliant, but you can see that for lower temperatures. Because of the Planck function, we allow higher errors in Kelvin. And again, you see the worst case performance and the typical performance. So most of the time we are on the magenta curve here, and we are much below the requirement. We have a requirement for medium-term radiometric stability. So it's the calibration stability for the Viz near. It's over a day, and for the IR is over a repeat cycle. So let's say 10 minutes for the full disk. So between one image and the next, we want a difference in the calibration of less than 0.1 or 0.2 Kelvin. We have the long-term radiometric stability. So that's the stability of the instrument over its lifetime. So we do not allow a drift of more than 2% in the Viz near, a drift of the calibration. And for the infrared channels, the drift has to remain below 0.3 Kelvin. We also have a requirement called radiometric accuracy, and this is basically the accuracy, the absolute accuracy of one given image. So it's the at any given time, our calibration needs to be below 5% for the Viz of normal resolution, Viz near, and below 0.7 K in the infrared. We also have geometric requirements, of course. So we have our very good radiometric measurements, but we want them to be well geolocated. So we want to know where we're looking at, basically. So we have a requirement called absolute pixel position knowledge error over an image. So for any image during our the lifetime, we will look at the worst case pixels within the image. Actually, we have this is 3 sigma. So meaning that we will look at the 0.3% pixels with the worst geolocation within an image, and they should be below these errors here. So for the images with 500 millimeter resolution, then we want to have a better geolocation than 0.75, so 750 meters. And so it's basically 1.5 times the SSD, the accuracy. But again, it's at 3 sigma. So when you will look at a typical pixel, it will be much lower than this. Okay, and this is the worst case image over the lifetime. We also expect the sequential acquisitions to be well georeferenced with each other. right? So for instance, when we look at the winds, we look at the differences, the movement of the cloud from one image to another. So you want those clouds to be well registered with each other. So these are the requirements. So we want a better than 1.05 kilometer, again at 3 sigma. And finally, we have also requirements for the relative position knowledge error between spectral channels. So we want the channels to be also well registered with each other. And those are, okay, we have a table, I won't go into it, but these are the requirements depending if we want to register a visible channel with a visible channel or with a thermal infrared and so on. You'll find all these values in the EURD. Last slides on the requirements. We have a few other requirements, which I will not elaborate, but I will mention them here. Spectral requirements. So of course, we want our spectral response functions to be uniform across the detector columns, because we have for one given channel, for instance, the channels with 500 meters, we have 440 pixels, right? And actually times 4 redundant columns. And we want the spectral response function to be uniform and stable over those pixels. We want to know the SRF very accurately, so that's the knowledge accuracy, of course, it's very important. And we have also what we call the SRF template, so the SRF, the spectral response functions, needs to be exactly where we have specified them. A really challenging requirement also is the timeliness, so that this is a requirement for both the satellite and the ground processor. It's actually very challenging for the ground processor. So the duration between the end of a repeat cycle acquisition, so once the satellite is finished, I mean the instrument is finished acquiring our full disk, so it's coming to the north of Europe, then it should be completely disseminated by 15 minutes for the full disk. This is the threshold requirement, and 10 minutes as a goal. And for the rapid scan, it should be within 5 and 2.5 minutes. We have not the final estimates for those, but so far things look good. But we had to work a lot on optimizing some of the really complicated and heavy algorithms to achieve that. A few other requirements which are not specified in the URD, but which are still focusing our attention, because we have negotiated those with ESA, and they are in a lower level document. We have a limitation of the sun's light, so we don't want the halo around the sun to be too big, too frequent. Limitation of the infill light. We do not want the light within the scene to be redistributed to a high level, let's say. We want to contain this. Stray lights are unavoidable with this type of optics, but we limit them by design of the optics, by the quality of the manufacturing, but also with algorithms, which are dependent also on the quality of the characterization on ground and in orbit. We have also requirement of the modulation transfer function, which what we call the MTF. Essentially, it's a measure of the degree of focus of the instrument. One slide before the conclusion, a summary of the differences of the performances between FCI and Severi. For Severi, we have a 15-minute repeat cycle. FCI will have 10 minutes. The noise, so the signal to noise ratio, is on Severi is 1.2 to 10.1, and again the higher the better here. So on FCI we'll have 12 to 40, and for the infrared, the lower the better. And the noise on Severi was 0.25 to 1.8 K, and the specified noise for FCI is 0.1 to 0.3 K. But as you saw, the measured noise is even lower. We have also an extended dynamic range for the fire channel, up to 450K, so we will saturate much less, as I explained. And for the resolution of the channels, we had, of course, the HRV channel on Severi, which had 1 kilometer. That was one panchromatic channel, but the 11 scientific channels were at 3 kilometers, right? Whereas for FCI, we have in what we call the full disk high spectral resolution imagery, so the full disk, 8 times 1 kilometer channels and 8 times 2 kilometer channel. In the HRFI, we have 2 channels of 500 meters and 2 channels of 1 kilometer. Katya later this afternoon will explain how those are disseminated and how we can access them. And of course, we have these 5 new channels on FCI as opposed to Severi. In summary, the FCI will continue the established services from Severi, and that's the first goal, of course. But of course, we bring enhanced capabilities, which are enabled by a state-of-the-art and much more complex instruments and processes, which will provide then societies in Africa and Europe with unprecedented information about severe weather. There will be a qualitative and quantitative jump in data volume, content, quality, and therefore in the potential for applications and products. There were a lot of challenges posed to European industry, which have done a fantastic job here, delivering these instruments and platform. But of course also for ESA and EUMETSAT to deliver the MTG system, so satellite and the ground segment. Let's not forget it. It's also extremely complex. The next step is the challenges for the users for their research and development. We anticipate it to be huge. First of all, to transition from MSG to MTG, but also to fully exploit the data. And my last point here is that MTG I1 and will complete the georing of the novel sensors with similar capabilities in 2022. So with this, I will complete the presentation. And I think it's time for questions, Stefan, right?
Yes, thank you very much, Munir. Great overview, and we're all very much looking forward to this new sensor. And it was great that you shed some light on some of the numbers and what the rationale behind them is. Thanks very much. We have time for
Thank you. 2
questions, but keep asking your questions via Slido, slido.com, event code #ng-images. I'll just share some of the questions that we have. Okay. Can you see my screen okay? So the first one here from Gerrit from DWD. You mentioned the performance of NEAR 1.3 as better than expected. What is the status of the NEAR 1.3 stray light problem?
Okay, so the performance that is better than expected is actually the noise from the channel. So the radiometric noise. Concerning the stray light, indeed we had a problem for this particular channel, and it's been addressed both by a very accurate characterization on ground with additional tests which have caused a lot of effort at ESA and industry side. We have very good characterization data to correct for the stray light. And for the part that is not correctable because it comes from a different band, we have a change of the design where we implement a mask of the channels. We fit a little mask on the detectors, but this can only be done on the recurrent models of FCI, so from FCI 2, 3, 4. So there will be an improved performance starting from the second mission.
Thank you, Munir. Let's take one more question. How do you switch the 1 and 2 kilometer resolution for the 3.8 micron and 10.5 micron band?
Oh, okay, so
you don't really switch. Yeah.
Well, I showed in the. Should I show my screen again, or probably would be?
Yeah, why not?
So I showed it in the level 1 processor. We have a step there in the corrections. Can you see it again? Yes. Before the
no, we can't see.
You cannot see. Sorry, I forgot to click. I forgot to confirm. You should see it now, right? Okay. So
yes.
In this type of the processing here, we take the low resolution or the normal resolution images, and we average them 2 by 2 basically. So we take 4 pixels and we make 1 pixel out of it. This is a simple description because in fact we apply also a focus MTF filter to ensure that the focus remains good and we have no aliasing. But this is essentially the step here. This is for the 10.5. For the 3.8, we have the same. But it's a bit more complex because we have before the merging. So what we do, we have the high resolution of the cold temperature and the high resolution of the warm temperature, and we merge them together into one channel. And then this merge channel then is it's provided to the users in high resolution, and then we also downsample it in low resolution.
Okay, thank you. With that, I suggest we stop the Q&A for the moment. Thank you very much, Munir, again. I suggest we take a 2-minute break just to stretch our legs and then reconvene with Katja's presentation at 14:53 Central European Summertime. So in 2 minutes, the level 1 data as they are presented to users. So I hand the floor to my colleague, Katja Hungershofer. Katja, you have the floor.
Yeah, thanks, Stefan. And hello to everybody on the line. I hope, can you just confirm that you see the presentation?
Yes, I can see it.
Okay, good. Then, okay, so this is a short presentation that introduces you to the basics regarding the FCI level 1 format and the dissemination. And hopefully it paves the way to the presentations by Andrea just after this one. So as already mentioned by Munir, we have the full disk scanning service with 10-minute repeat cycles, scanning the full disk, and we have the rapid scanning service providing measurements every 2.5 minutes by looking at the north quarter of the disk, which is also called LAC44. In case you are not yet familiar, LAC stands for Local Area Coverage, and it defines a sub-area of the full disk. So as you can see on the figure here, the LAC1 is basically the full disk, and the terms LAC2, 3, and 4 correspond to a separation of the full disk in 2 halves, 3/3, or 4/4 respectively. And in all these 3 cases, the LAC is numbered, just a second, from north to south, starting from 1. Okay, format specifications are a family of very important documents for us because they contain the format description of all the level 0, level 1, and level 2 data. They have evolved with the increasing functionalities of the processing algorithms, and we have reached a quite mature state for the FCI now. For each development stage of the operational ground processing, we have defined a specific format version. And this is important to ensure that our interfaces are working correctly. For example, you can imagine that the FCI level 1C outputs generated by the level 1 processing must have exactly the same format that the level 2 processing facility is expecting, because otherwise we will be in trouble. So to keep your life easy, we have collected the information relevant for you from the several format documents, and we merged them together with additional information about processing specifications in the so-called FCI Level 1 Product User Guide. And for this, we have used the latest available format specification in order to be as close as possible to the format that you will receive in operations. For the African users, an additional document exists, and I will come back to this later. Here's just an example. Within the product user guide, in the appendices, you have these tables describing the format with the names and the dimensions and everything. The most interesting FCI level 1 dataset for users is certainly the level 1C, as mentioned by Munir, because it contains the rectified radiances, that is the scientific data rectified to the reference grid, together with some auxiliary data about processing configurations and also quality assessment. Normally, one FCI level 1C dataset covers a full repeat cycle, and it is divided into a series of individual files. We also call them chunks. So the main bulk of the dataset, you will have a series of so-called body chunks that contain the radiances, for example. And in addition, there's normally one trailer chunk that contains information applicable to the whole complete cycle. So for example, there you would find the name of all body chunk files that make up this repeat cycle. The data chunks are named as per standard WMO naming convention. They are formatted in netcdf, and they use a so-called enhanced data model, meaning that within the product, you will find different groups. The CF convention is followed whenever possible, as well as the NetCDF attribute convention for dataset discovery. Here you see example FCI level 1 file names for one repeat cycle. And as part of the file name, you have the spacecraft and the instrument indicator. You will find the processing level, the data type, and the coverage. Here you will see that the data is chunked, and as you look carefully, you will find 40 body chunks for one repeat cycle, and then this additional trailer chunk that I've just mentioned. In addition, we have the generation time, and we have the sensing start and end time. Here at the end, the first counter is the repeat cycle counter per day, and it indicates the current repeat cycle in the given day. So it starts at 1 for the first repeat cycle at or just after midnight. So here in our example, you see it's the second repeat cycle, so from 10 to 20 past midnight. And the second number is the chunk counter within the repeat cycle. So this counter will have discontinuities, for example, when chunks are not produced or when there's a problem in dissemination. This counter starts as well from 1, and it is resetted when the first, so the repeat cycle counter changes as value. Okay, when you open one of these body chunk NetCDF files, you will find the following structure. This is the enhanced data model. And for example, the radiances that you are probably most interested in, you will find them in the group data channels measured, where the channel is replaced by the actual channel name. That means that the information for all channels is stored in one file. Okay, the same is true for the trailer chunks. So for example, here in the root, you will find the body chunk names as I mentioned before. So that's it about the format. Now let's move to the dissemination. So the MTG datasets and products that will be disseminated and archived at EUMETSAT are defined in the so-called MTG DIS document. The current version, approved by Council in December 20, defines the products for the time when we start operations. That means after successful MTGI commissioning. And after this, of course, we expect an evolution of this baseline due to developments and new and enhanced products. For the dissemination, we will rely on existing mechanisms. Those are the EUMETCAST Europe and the EUMETCAST Africa using telecommunication satellites. We have the EUMETCAST terrestrial and a bundle of specialized networks. The EUMETSAT data store is your interface for online retrieval via internet and will also provide you with older archived data. We will start with the full disk scanning service, as Munir mentioned, with the first MTGI satellite. So there we have the 16 FDHSI channels with a 10-minute repeat cycle, and they will be disseminated via EUMETCAST Europe, EUMETCAST terrestrial, and the others listed here. For the 4 channels where we have a better spatial resolution, this HRFI channels, they will only be provided in EUMETCAST terrestrial. So please be aware that in case you want to use them, you have to make sure that you have access to those. They will not come via the EUMETCAST Europe. So once the second MTGI satellite is commissioned, the wrapping scanning service datasets for the leg 4 will also be disseminated with the temporal resolution of 2.5 minutes. And in this case, the data will be available via EUMETCAST Europe, as you can see. One important note, for the real-time FCI level 1C data, this is compressed in order to meet the requirements for the bandwidth. And Andrea will tell you more about this KLS algorithm later on. Okay, the products disseminated to the African end users are described in a dedicated document, the MTG EUMETCAST Africa Product User Guide. Here we divide between 2 sort of groups. So we have the native products, which are standard MTG products without modifications. And for those, the African Product User Guide simply refers to the FCI Level 1 Product User Guide because there's no change. And the second group are customized products specially tailored for the end users in Africa. And those are described in more detail in the African Product User Guide. Since my time today is limited, I cannot go into the details for all the African products, but what I would like to propose to you is there was a dedicated webinar focusing on the African products, and all the presentations and the recorded presentations, then you can find them here in this link. Okay, so these are the references for the documents that I've used in case you want to have a look later on. And this is from my side, so thank you very much for your attention.
Thank you very much, Katja. Great overview. I hope people find it useful, with very practical information. Let's treat a couple of questions. And okay, so we have this one here, which I think you answered, but I still pose it. What is the format of level 1C data?
It's NetCDF.
Will the level 1B data be available to users?
No.
Simple. Oh. Okay. We have many other questions. Oh yeah, this one. Is this correct? Level 1C data for, oh, it's moved. Is level 1C data for FCI the same as level 1B data from MSG, Severi?
Yes.
Okay, I think we have to move on. We'll take more questions later. For the moment, we stop it there. Keep asking your questions via Slido, #NG-images. And with that, I want to thank you, Katja, for your time and move on to the next presentation by Andrea Marana from EUMETSAT, who will speak about the details of the level 1C dataset, the compression algorithm, and then on the test data that has been released so far to help users familiarize. Andrea, the floor is yours.
Can you hear me?
Yes.
Okay.
Good.
Oh, okay. My Zoom just crashed, so I hope
You're okay. We just
working.
presentation mode.
Okay.
Very good.
Whew. Everything turned dark suddenly. Okay. So hi everyone. I'm Andrea Marana. I work at EUMETSAT as a junior remote sensing scientist. And as introduced by Katja already, I will show you the characteristic of the level 1C of the level 1C data set and its usage, and give you some instructions on how to extract interesting data, etc. So I will present the slides, but they have been created together with my colleagues Munir, Katja, and Stefan that you have already met during this presentation, as well as Sauli Yoro. Okay, so we have been talking about chunks during the last presentations. I will just explain a bit more the concept of them. So as we have seen from Munir's presentation, the image data is actually acquired with a scan pattern in east-west direction and south-north. And as the data from the scans come in, we start producing these data chunks. So we produce 40 body data chunks, and they are basically rectangular blocks of data, similarly to what Severi has in the HRIT format, basically. So we basically take the SWAFs data and we rectify and resample them into a fixed grid. I will talk about this fixed grid in the next slides as well. And once the pixels have been placed into this fixed grid, we can start producing these chunks. And the chunks cover the full horizontal extent of the image, so that by simply stacking vertically the different chunks, we can compose the full image. And the data chunks have regular sizes in the vertical direction, and we tweak the size and we tweak this data chunks production to optimize the timeliness of level 1C, of the level 1C data delivery. Okay, so as I mentioned, the level 1C data sets are stored in a static reference grid, which means that every pixel in each level 1C image for each repeat cycle will always show at the same position in time. And all the movements and deviations from the satellites are accounted for and are corrected during the rectification. So this grid is square, and it has several thousand pixels of size for each side. You see the precise numbers there. And the reduced scans, as we have seen, for example, the RSS dissemination, are defined as subsets of the full disk grid. So what is actually this grid? So we say that the data is in the normalized geostationary projection. So this projection is describing what an idealized satellite at an idealized stable position over the equator at longitude 0 sees of the Earth, and the Earth has also an idealized ellipsoid shape. And we create this reference grid by letting our idealized satellites scan the Earth in regular azimuths and elevation angles. So the azimuth will be the horizontal direction, the X direction, and the elevation will be the vertical direction, so the Y direction. And by putting together one pixel for each of these scan angle step, we can create the grid. So as the grid is defined by regular angles steps, everything that we need to define the grid is two 1D arrays. So these 1D arrays are actually placed, are present in the product, of course, since you'll need them to compute the geolocation. And they are specifically in the data group for each channel, inside each subgroup for a channel, in the measure group, and they are called simply X and Y. X for the azimuth and Y for the elevation. And the arrays as they are stored in the NetCDF are simply integer arrays that contain the column and row number of each pixel. So as we see in the image on the right, the origin is in the southwest corner of the image, and the index starts from 1. And by spanning the two 1D arrays from 1 to 5,568, for example, in this 2 kilometer grid, in both directions, we can create the pixel grid. But now we have been talking about the unpacked X and Y arrays. So how they are plainly stored inside the NetCDF. To actually use them, we have to unpack them by the typical workflow, which is just multiplying the scale factor attribute of each of the array and adding the add offset of each of the array. Many NetCDF libraries do this actually automatically. So by multiplying the scale factor and add offset for X and Y, we get the azimuth and elevation coordinates each, respectively. And here it has to be noted that the coordinates that are extracted this way describe the pixel center position. And please also pay attention that in this case, the azimuth angle is defined as positive in west direction. So as you see in the plots on the sides of the grid, the X array goes from positive to negative values. The azimuth goes from positive to negative, and the Y array goes from negative to positive values. If you want to take this azimuth and elevation and compute actually the longitude and latitude, which is often more useful, you will have to apply a few formulas. They are available in the FCI Level 1 product user guide we have seen mentioned by Katja. Or you can let code libraries like Proj do the conversion for you using the normalized geostationary projection. And you will need a couple of more parameters to compute the projection. So for example, the satellite height, the Earth size, and so on. And these parameters are all stored in the data MTG geos projection variable inside the netcdf. For validating your algorithm for computing the geolocation and the longitude and latitude of each pixel, we have also distributed in the last test data package, I will talk about later, some pre-computed lat and long grids so that you can check your computation with those. Okay, so now let's look at 2D array data. So basically the image data that is stored inside the level 1C netcdfs. So what you see now here is just a screenshot from Panoply. I opened one of the chunks, and in the group data, you will find one subgroup for each channel. So for example, here I'm looking at the IR 10.5. And inside each channels group, there is a group called measured. And here is where all, let's say, juicy data is stored. So we have the effective radiance, so the image data actually. And then we have the index map and the pixel quality. And now I will go into each of them. So let's start with the effective radiance. So the image data is stored inside the file in integer counts. This is very usual in the satellite data world. And for FCI, we actually use 12 bits to store the integers. And by unpacking, again, using the scale factor and odd offset of the effective radiance values, you will get the radiances in radiance units. In this case, milliwatt per square meter, steradian, and wave number. There is a special case, as mentioned by Munir earlier. The 3.9 channel is actually at instrument side. It's split in two. We have two detectors that cover two different ranges of the radiances, and in the level 1C products, the data from the two detectors is merged into one. So this has to be taken care of when you try to read the 3.9 channel out of the files. So yeah, as mentioned by Munir, we do this extended dynamic range to avoid saturation with very high temperature hotspots, so typically fires. So in this case, the values, the count values for the 3.9 channel are actually 13 bits. So there is one more bit. And for all values between the 12th and the 3rd bit, so basically all values above 4095, you will have to apply a different scale factor compared to the other channels, which is called warm scale factor. and also the same for the odd offset. So in this case, warm odd offset. So for every channel, you need to use scale factor and odd offset. But in this case, for count values above 4095, you have to apply a different scale factor and odd offset to compute the correct radiances. And pixels that are outside of the disk or invalid, we fill them with the fill value of the variable type. So if you want to convert the radiances to reflectances, specifically for the vis-near channels, or to brightness temperatures for the infrared channels, you will have to apply against a couple of formulas. They are available in the product user guide. And for this, you will need a couple of coefficients, and they are stored close to the effective radiance inside an SCDF, as you see here as marked in red. Okay, so the next 2D array we're going to look at is the pixel quality. As the name says, it's an array that describes the quality or warns users about problems that could have been occurred during the processing of each pixel. It's a bit mask with 8 bits, and it contains therefore basically 8 warning flags. So for example, there is a missing warning if a pixel was not available for during the rectification process. There is a warning for radiometric problems, a warning for high noise, a warning for problem in the geolocation, and again the saturation when the signal has reached the limit of the pixel value. There is stray light correction warning. So it tells user where solar stray light have been affecting specific pixels. There is an extended dynamic range warning, which tells you that this pixel has contributions from this extended range from the fire channel. And finally, again, a flag for the encoding saturation. So if we look at an example, if you find a pixel in the pixel quality that has value 22, you will need to convert this in binary in a binary number, which is shown here, and then you can spread this binary number starting from the right-hand side number along the pixel quality bit mask values, and values that have been marked by 1 signalize that this flag has been activated for this pixel. So for example, here, if the pixel has number 22, then it means that the radiometric, the noise, and the saturation flags have been activated. And okay, so the next one up is the index map. This is a new concept, at least here at EUMETSAT, so it needs specific care. So what is the index map? Basically, it's again a 2D array, so every pixel gets a value, and specifically, every pixel in the level 1C grid receives an index, as the name suggests. And this index basically shows or indicates the number of fixed time periods, so the number of fixed time steps that have passed since the start of the repeat cycle. So for example, if the index map has been tuned to show an index every 0.1 seconds, an index value of 20 means that this pixel has been acquired 2 seconds after the start of the repeat cycle. So as you see, we can tune this index map to have a different precision or time resolution. For now, we are using 0.1 seconds. So since the repeat cycle takes 10 minutes and there are 60 seconds in 1 minute, we have 600 seconds for one repeat cycle, which means that we have 6,000 indices in each index map, 6,000 possible indices. And why do we do this? Actually, we do this index map to assign specific parameters to each pixel. What do I mean by this? So associated to this index map, in the level 1C files, you will find several 1D arrays, so 1D vectors, that store time series of geometric and acquisition parameters. So, for example, on the table on the right, you see the subsatellite latitude 1D array. So, by using the value of the index value of each pixel as an index inside this time series, you can assign, or you can find out which parameter from the geometric or the acquisition properties is valid for that specific pixel. It's basically a lookup table. You can think it as that. So you can use the index map value to find out which geometric value is applied or is applicable for a specific pixel. And so it's basically an optimized way to deliver geometric and acquisition parameters for the full disk while saving memory and at the cost of reduced resolution. So for example, here we have a 0.1 second resolution for each index map parameter. So you will only get steps of 0.1 seconds in the acquisition. Okay, so let's look at these parameters, how they look like. So as you see, there is a list of parameters that can be used with this mechanism. So there is the index map, and if you use the index map together with the variable data swap direction, you can find out in which direction in each direction of the scan, in which direction of the scan this pixel has been acquired. So you will have 0 and 1 for east-west or west-east scan direction. And in this way, you can also find out the swap number for a specific pixel, the time. So again, the acquisition time in seconds since the 1st of January of 2000. Then there are a couple of, say, celestial parameters. So for example, the sun satellite distance and the Earth sun distance for each pixel. And there is the position of the satellite above the Earth, expressed in latitude and longitude. Then there is the subsolar position in terms of longitude and latitude on the Earth. And finally, the altitude of the satellite. So these are, of course, of interest only if you really want to take a close look at the data. And you can use these parameters to do a precise calibration or any kind of further processing you might be interested that depends on these variables that we see here. Okay, as mentioned by Katja, in the near real-time dissemination, the level 1C chunks will be compressed. And for the compression, we use a specific algorithm, which is called CARLS. It's lossless, and it's based on the JPEG 2000 algorithm. And so as we see in the graphic, the compression ratio is better than Zetlib, for example. and it's also faster as we have assessed in some of the studies with similar satellite data. So what does this mean? You basically inside the files there are 2D arrays that we have seen until now, so the effective radiance and the index map and the pixel quality, and these 3 variables are compressed. So even without compression, you are still able to access the rest of the netCDF. But if you want to read the 2D array, you will have to run the decompression first. And to do this, you will need netCDF, and you will have to install the plugin for CarLS. So this is open source, and so there is a library and a filter that you can install, and they are both available. And it currently requires an HDF version of 1.8. So the package for installing this CarLS is available on the EUMETSAT webpage. I will give you the link shortly. And yeah, as you can see, it requires some older libraries and some specific installation. So we are still working on this, and we will release updates in the future. And yeah, so stay tuned on this. Okay, so that was the end of my first presentation about the properties of the level 1C. Stefan, if you agree.
I suggest we move on and finish your presentation and then take a few questions.
Okay, very well. Okay, so this part of the presentation is about the test data sets. So specifically the level 1C test data sets that EUMETSAT has released in the last years. And then after it, we will also have a SatPy reader demo. I will show you. Explain that. The last one that we released is called Enhanced User Familiarization. We released it in the summer of last year. And well, you can find everything. So the data, the description, the user guide for it, etc. on the EUMETSAT webpage, and it's available to SFTP download. So what does this test data set contain? Well, most importantly, it's in the FTHSI imaging mode, which means that it contains full disk of data and the normal resolution. So 1 kilometer and 2 kilometer grids. It's only one repeat cycle, so only one timestamp, and you see the dates on the slide. We provide this same repeat cycle in different versions. So there is a nominal and non-nominal acquisition mode. I will explain in the next slide what non-nominal acquisition means, but it's basically a simulation of a corrupted acquisition. And we also deliver, or the test data sets contains both the compressed and uncompressed data. So even if you don't have the CarLS running yet, there is the uncompressed data that you can use as is in plain netCDF format. The main focus of this and all the last test dataset releases is the format. So to give you users the possibility of getting acquainted with this group structure, with this chunk structures, etc. The geolocation, of course, as well, and so on. And so the focus is not so much on the scientific content. Well, so about this, about the input scene, so what data is actually contained inside. So for the heritage channels, it's simply Severi images. So all channels that are available in Severi, we basically just copied them inside the format for the FCI level 1C and did a simple resampling to get the right image array sizes. So the spatial resolution the real spatial resolution of the data is still the Severi one, even though the number of pixels is from FCI. And for the channels that are not available in Severi, the few new ones that we have, we put some radiances that we have simulated using different techniques. So we use ACM-WF forecasts together with our TTOVs and cloud properties from Severi to try to simulate a channel, the FCI channel starting from the Severi, so from the Severi information that we have. Okay, so about the features of this specific test data set. As I mentioned, there is a refill cycle also in non-nominal mode. So as you see on an RGB on the right that has been created with this data, there are obvious gaps inside the data. So we simulate transmission errors, transmission stuff from the instrument, so that we lose some of the acquired pixels. And these pixels are then, of course, they are not available, so they are filled with fill value inside the data. So by using this data, you can set up your system to cope with this kind of data gaps. We populate the index map and the geometric data that we have seen before. In fact, the images you have seen before about the index map and all the parameters have been created from this data set. And we also populate the pixel quality flags as far as they are available. We also populate the radiometric noise lookup tables that can be found in the product. And finally, we simulate some fire pixels in the 999 channel, and specifically to fill up the 888, sorry, to fill up the extended range of the channel so that you can train the usage of this warm scale factor and warm add offset to extract the correct radiances and temperatures for high temperature fires. And about other test data sets that are available. So in the past, we have released 24-hour data sets to users, specifically, now 2 years ago. So this contains 24 hours of data, one repeat cycle every 10 minutes. It's still Severi simulated data. So yeah, nothing new there. But pay attention that this has an updated format with 70 chunks, while in the meanwhile we have moved to using 40 chunks. And so we plan to improve the test data sets and release new ones in the future, of course. And it's quite exciting. We have some plans to generate it fully simulated and spectrally representative test data sets. What do I mean by this? So we have the study that's delivered a hyperspectral data cube of synthetic top of atmosphere scenes for the full disk. So basically we have the full disk view, and across a number of very thin channels in the spectral domain, we have simulated the radiances for it. I think we have around 10,000 channels in the range of the FCI acquisition in terms of spectral range of the FCI acquisition. So basically, by taking the spectral response functions from FCI and convolute them with this hyperspectral dimension of the data cube, we can compose FCI channels that are spectrally realistic, and so that have some more value on the spectral side. Of course, still This data has also been produced starting with Severi as a proxy, so the spatial resolution will still be the one from Severi. So yeah, we invite you to stay tuned and look for updates about test data sets for FCI level 1C soon. And as a final slide, the reference for what I've talked about. So there is an MTG test data page in the EUMETSAT webpage. And here you can find basically all I've talked about. So specifically the last version of the product user guide. You can find a link to the test data packages and also a link to the CarLS software package. Okay, the next part of the presentation will be the SATFI demo. Stefan, what do you say? Should I go on?
How long do you need for that?
I think, yes, somewhere between 10 minutes, 10, 15 minutes.
Yeah, I suggest we combine it with the SIF demonstration. So
Okay,
we take a few questions now, we take a short break, then we resume with the demo. Okay, thank you very much, Andrea, for this insight on the details of the level 1C data set.
Thank you. Thank you.
I'll share the questions that we have. Before I go into the questions, I'd like to remind you that we would like to hear from you about your feedback on this webinar. On Slido, in the same area, we have a poll which we ask you to respond to. It's 5 quick questions, and that would help us know where we are with these webinars and improve them in the future. So after the webinar, please respond to the poll. We do 1 poll for each day of these webinars. Let's see what we have. Perhaps questions that are directly relevant for Andrea. This one we can take. All right, let's take this one. Will the digital counts from the sensor be available directly or indirectly in the level 1C data?
So if you mean the digital counts that come directly from the sensor, so to say at level 0 level, then no, as far as I know, we are not gonna disseminate these. The digital counts that you find in the level 1C data are already calibrated so that by applying the scale factor and an offset, you get the radiances out, and then afterwards the reflectances and the brightness temperatures. Yeah.
Okay. And this one is one for you, Andrea, also from Martin Ruspo. Thanks for your questions, Martin. Does the discrete nature of the index map imply that the resampling of level 1B to level 1C is using a nearest neighbor approach?
I would say these two things are not related. So the discrete nature of the index map is just a parameter that we can tune to decide how precise and then therefore how big the arrays can be for extracting these geometric and acquisition parameters. But the resampling from level 1B to level 1C has basically nothing to do with this. It's not nearest neighbor approach, as far as I know. It's using a neighborhood of pixels for the rectifications from level 1B to level 1C. Yeah, I don't know the details of the exact algorithm here. But yeah, I think the question is no, because the two things are not directly related to each other.
Okay, if I understand correctly, the 0.1 second discretization is somehow a compromise on the size of your lookup table versus the accuracy in which you can determine these parameters for each pixel, correct? So if this temporal sampling was higher, then the precision would be higher, but then your lookup table would grow.
Exactly.
Exactly. Yeah. Okay. Okay. Thank you very much. I suggest we take this one is important. Will the CARLS? There's lots of questions about CARLS that we get on the test data sets. Will the CARLS software be available as a DLL for Windows or in SatPy?
So currently it's only available for Linux, as far as I know. I don't know if there are plans to make it also available for Windows. And in SatPy, yes, it will be available. It is just a matter of installing the filter and all the libraries in the correct way, so that SatPy can make use of them and decompress the data on the fly. So this will be or is integrated in SatPy already.
Yes, I can confirm there are, let's say, considerations of making the solution available for Windows. I mean, there are possible developments which EUMETSAT has looked into, but it's not something that we have currently committed to do. There are, theoretically, you could have a Docker implementation where the library is available, but that hasn't been realized yet. So it's the short answer for the moment is no. All right, I think. Right, let's take this one more. We've covered this question. Let's take this question from Garrett as the last one before a short break. What is the timeline for an updated CARLS plugin working with recent versions of libraries?
Stefan, you want to take that?
Yeah. There is no current time plan. We are looking into ways to make CARLS compatible with more recent versions of the libraries, and that it becomes part of the standard distribution of HDF. But that's currently only under consideration, and there's no currently firm plan. Okay, with that, I suggest, so I'd like to point out again, we're interested in your feedback on the webinar through the polls, either now or later. Thank you very much, Andrea, for this first part of your presentation. I suggest we take a 4-minute break until 15:50 Central European Summer Time. So 4 minutes break and then be back for the demonstration of SIFT and SatPy. And then we finish with a great presentation by Vesa on applications, use cases for the new channels and the evolution of RGBs. So stay tuned. Thank you. Spectral images operated by EUMETSAT on the MTG and EPSSG next generation programs. So we'll resume this session with the last block of presentations, the first by Andrea Marana, who's providing a demonstration of some of the processing and visualization tools, and then a presentation by our trainer Vesa Nietosvara on use cases for new channels, RGBs, and their evolution. So Andrea, you have the floor.
Thank you. Sharing.
Andrea, are you there?
Can you see me now?
Yes. Well, not your slides yet.
Okay. Can you see my slide as well? Not my slide. Okay. Again, I had this glitch that Zoom turned black. I will try again. This always happens at the wrong moment. Okay, I think it should be working now. Okay, so the next part of this presentation is about two demos. So I will start with a demo of SatPy and the reader for the FCI Level 1C dataset that is available in SatPy. Okay, so first of all, what is SatPy and what is Spectral? So Spectral is a collection of free and open source software written in Python, and it contains a whole list of tools that can be used to process Earth observation satellite data. Really from all aspects, starting from the ground station reception handling up to the product generation. All modules are quite easy to use, and they can be used both for scientific purposes as well as for operational product generation. So one important part of Spectral is SatPy. Since SatPy is the library that is delegated to read and extract all data from satellite files. So it's quite a high level and so also very easy to use. I will see in a moment. It supports a whole list of satellite products, both from GEO and LEO satellites and sensors. It can read many input formats from this specific from this list of satellites. It can also, of course, write what has been read and processed in several formats. It offers also the capability of create composites and RGBs in a built-in manner, so the user has very little work to do to create these RGBs. And it offers the capability of resampling together with PyResample, another package of Spectral, and basically to any projection available in Proj, and much more, corrections, calibrations, and enhancements, and so on. So the entire all Spectral packages are open source, so it's quite an open community and very welcoming for contributions. And so just feel free to check the web pages I see here, and go also to GitHub to see the code. And if you like to add new features, you're very welcome to contribute. Okay, so basically the only step that is needed to use SatPy is to install it. So pip install SatPy, and this brings me to my demo. I quickly have to change screen. Okay, there you go. Okay, so you should be seeing my my IDE, my coding software, and I prepared a little code snippet that does some common operations that are available on SatPy, and I will apply everything to the test data sets that we have seen in my previous presentation. So the so-called user familiarization, enhanced user familiarization test data set. And yeah, so I would say let's just start. I will run this code basically line by line, so telling you what is going on and what SatPy is doing in the background. So I will just ask you to follow my code execution as we go along through this demo. Okay, so let's start it. As any Python module, we'll start with the import. From SatPy, it's actually just one. So it's we need the scene class from SatPy to start with our code, and that's also everything we need. I'm just using glob for extracting file names and the OS library to create the file paths to my files. Okay, so the first step I'm doing now is just telling SatPy where to find my test data. For now, I'll just use the nominal acquisition mode that I've described before, so the one without gaps, in the uncompressed version for simplicity. Okay, so the first step that you need to do when trying to load or to read something from a file is to initialize this scene, a scene object. So what the scene needs is the list of file names that you want to read. So here I'm just taking my folder and I'm extracting all body chunks that are available inside that folder, and I'm passing them to the scene in the file names keyword argument. And the other thing that the scene needs is the reader name. So in this case, we are using the built-in reader for the FCI level 1C netcdf dataset, which is called very, very simply FCI underscore level 1C underscore netcdf. And okay, so I will execute this command. What SatPy is doing now in the background is it's basically taking all the file names that I've given him and opening them, looking inside them, trying to figure out what can be done with the file names, what data is available in the file names, and what is possible to do. So now let's see what he found out. So I'm just gonna I'm going to the console here on the right, and I'm gonna just look at what available data sets that SatPy has found in the scene. So for doing this, I define simple variable and I look at my scene object. And as my IDE suggests, there are a couple of methods that can be applied to the scene object. Specifically, we are going to look now at the available dataset names. So we want to find out what can be found in the scene. I repeat, like right now, SatPy has just looked inside the files just to figure out what's there. He hasn't done anything more. So let's explore this variable. It's a simple list. It's quite long, 208 elements. So the current implementation of the SatPy reader is already able to read a lot of things. So let's look, for example, of course, there are all channels. They are called the same way they are called inside an SCDF. So it's spectral range, IR, near, or vis, and then the wavelength. So for example, there is the IR 10.5, and additionally, also other things are available and can be read. So for example, there is a pixel quality we have seen before, there is an index map, and there are all the other parameters that are associated with the index map. For example, the time and so on. So basically all the lookup table operations that I've shown you in my previous presentation, all the reading index map, assigning it to the lookup table and extract all values for each pixel, this is all implemented inside SatPy. Okay, so let's just try to load one of these data sets. In my code example, I just picked the first one, so the IR 10.5. Let me go back Yeah, okay. So in this line now, I am calling another method on the scene, which is called load. So as the name says, it's designed to load the data out of the files. I define the name of the data set that I want. Here I call it by name. I could also call it by its wavelength, so index it by the wavelength. And I pass here an optional argument, which is called upper right corner. So the data inside the files is actually stored upside down, because as we have seen in one of my previous slides, the origin of the grid and of the indexing of the grid is placed in the south west corner. So basically, the entire data is flipped upside down, and if you just read the data as it comes, you will get the upside down image. By telling SatPy that please put my upper right corner of the image in northeast direction, so the usual upright position we are used to look at, SatPy will automatically in the background flip my data and show it as I want it. Okay, so let's execute this command. Now actually SatPy is taking this instruction and is actually going back to the files and starting to load the data out of the to open the files and look at the data. It also computes automatically, of course, the geolocation of the data. So all these X and Y operations with scale and offset, they are computed automatically inside SatPy and the reader. Okay, so it has finished. And let's just look at the data. So there is a very handy command, which is just show. So show me this data set. I'm running this. And there you go. My image shows up. So it has read all the chunks. So it's the complete disk that we see here. And it's showing me the 10.5 channel that I have requested. Okay, so I will now look at, okay, Stefan is asking me to speed up a bit. Okay, I will try. Okay, so I will just go on like now. If you actually are interested in the values of the array that we have just requested, you can access the array from the scene as a dictionary. So using the name of the data set as a dictionary key and extracting it from the scene, and then call the dot values and let's see what is available in the debugger. Here we go. It just gave me the 10.5 value array. I can open it and I can look at the data. As you can see, these are actually already Kelvins. So by just telling SatPy to load a data set, it will automatically give you the highest possible calibration that is available. So for an IR channel, the brightness temperatures, for a visible near channel, the reflectances. I will show you in a second how to get radiances or counts out. There are also, attached to the data set, there are several attributes that you can explore and you can use. One of them is the area attribute. It contains all information about the geolocation, so the area that SatPy has just computed for us to geolocate the data. So by just calling from the area attribute, the getLonLats method, SatPy will compute and give you the lons and lats in degrees out of the array. So it is calling in the background proj to compute the geostationary projection and get the longitude and latitude. We see the values have appeared here. So again, space pixels are infinite, and we are here looking at the latitude. So by going up, I reach the maximum of the full disk view around 80 degrees. The 80 degrees north, of course. Okay, so as I mentioned, by just telling SatPy to read something, you get the highest calibration. But if you are interested in the radiances or the counts, you can just add another keyword argument telling him the calibration that you want. For example, if I do radians, then SatPy will go again to the files and open and get me the radiances out. And yeah, the same way, basically we can open any other data set that is available, the ones that we have seen before. And yeah, so we can extract the index map, the time, the pixel quality, the exact same way as we have been doing until now. And also getting the values out of the data set can be done the same way. Here it's maybe interesting to know that SatPy uses X-array to pack this data set, the data inside the data set with coordinates and attributes. And the data layer of the X-array is actually using the Dask library. And this Dask library implements the lazy reading, which means that SatPy is actually loading the data inside your computer, inside your RAM, only when you are actually requiring it. So for example, when you call the values, or when you want to plot an image, or want to save the data inside another file. But until you really request the data, SatPy will not load it. And when it loads it, it will do it quite smartly. Since it will implement parallel processing, it will try to manage your available memory efficiently, so that you can read big amount of data or big files, even if you have a smaller computer, basically, or not such a powerful computer. Okay, as I mentioned, a nice feature is also the loading of composites and RGBs. So this happens by just telling SatPy which composites you want to have. And for example, here I'm loading the air mass RGB, and SatPy automatically knows which channels are required. So it takes them, it computes the calibration, the brightness temperatures, it does the channel differences if needed, it does all the computations and corrections that are needed, and gives you back the RGB array. Of course, this takes a little bit of time. So okay, there you go. Again, we can show what we have just loaded by just calling the show argument, the show method, and an image shows up. Okay, let's go through this as well. Here I'm loading another composite. It's called Day Macrophysics. This one is a little bit trickier because it combines visible channels and IR channels. And
Andrea, sorry.
Yes.
Could you cover the SIF demo also within 5 minutes, because we slowly have to move on. This is all great stuff because we need to know about SatPy, and you've shown the capabilities already. So try to finish this one swiftly and do the SIF demo real quick. Thank you.
Okay, yeah, sure. Yeah, so now I'm loading another composite that has channels in a different resolution. So to put them together in one image, we need to resample them. And so this is what I am doing here. So I'm taking my scene. I just go on in the meanwhile. I'm taking a scene and I'm calling a resample method on it. And here I'm defining to which area I want to resample. So there are a list of available areas. This one is Europe in 1 kilometer resolution. And by just telling SATPy, please resample my array to this area, it will just do it automatically. Here I'm using the default method, which is nearest neighbor, but there are a whole lot of resampling methods available. So yeah, here we get a nice picture of Europe and the day microphysics. And finally, you can, of course, save what we have done until now. There are many formats that you can use. Here I'm just using calling a plain PNG, but you can save to NetCDF. You can save to TIFF. Yeah, there are a wealth of formats that you can use. Okay, so let's just have a look at SIFT. So while I fire up SIFT, I introduce it by just saying that SIFT is a visualization software. It has been originally developed by the University of Wisconsin at Madison, the Space Science and Engineering Center. And again, it's free and open source. It's written in Python. And EUMETSAT has taken SIFT and is developing an enhanced version, a new version based on the development so far by the University of Wisconsin, and we are adapting it for what we need for the MTG program. So specifically, we are improving the interface of SIFT with Spectral. So SIFT in the background uses actually SATPy to read the data. And we are implementing the visualization of Leo data and point data and yeah, a few improvements that enhance this tool. So let's just see this quickly in action. I'm opening the wizard. I'm selecting the level 1C FCI reader. I quickly browse to the test data. I select all of the 40 chunks. I click next. Now in the background, again, it's trying to find out what is available for loading. So here we get the list of chunks. And let's just quickly load a couple of them. There you go. Click finish, and now SIFT is calling SATPy in the background, basically the same way we have done with in my previous demo, and is extracting all the values, doing the calibration, and preparing them for visualization. So we have to give him a few more seconds. And as you will see in a second, it's very fast. It uses GPU integration for the tiling and the visualization of the images. So once everything is loaded, it's quite impressive how fast the usage of the tool is. And so yeah, as you can see, the scrolling and the zooming inside the data is smooth and fast. And there are a few features. So for example, you can load different speed cycles and show an animation of the data. You can probe your data by clicking here on the point, and you can read the values of the data that you have just loaded inside here. And you can analyze, data is coming in. You can analyze different regions and create histograms of what you're looking at. yeah, and as you see here, it also shows you the values automatically for all the channels that we have loaded until now. One more thing to show is the reprojection. It's also incredibly fast. So for example, here I'm switching between the Severi IODC and the FCI view. There is also plate carré and basically any other projection. So it's extremely fast and easy to use if you want to explore your data. Okay, that's it. I think this is the most important part. Sorry if I took longer than expected. I'll stop sharing. Okay.
Thank you very much. This has been great, and I think many participants will appreciate the hands-on nature of your demo. And both tools that are related are really useful. They're open source, and we plan to make those available as open source software, with all the caveats on support, of course. So let's have a quick look at a couple of questions. The none related to this particular part. So I suggest then we move on to the last but not least, the wonderful presentation by Vesa Nyetoswara, who will give us some application perspectives of the new data that we should expect. And after that, we take 10 minutes at least for Q&A to answer many of the good questions that you've raised on the Slido. And we finish about a quarter of an hour later than expected. I hope this finds your understanding. And with that, I'd like to hand over to Vesa.
Thank you, Stefan. I hope you are seeing my slide fine now.
See it.
Good. So yes, good afternoon. And yes, it's a bit late for all, but I'm trying to somehow show you some of the excitement we have about the new upcoming products that we have together with upcoming MTG FCI. And while we are also excited about the new things, we have to also remember there's a word heritage data, and it's the legacy of the MSG. The satellite generations, they tend to change in a certain pace, and the people's minds change even slower. So I am still remembering very much the first generation of the Meteosat satellites and how they were impressive. And then came the MSG, and it took quite many years until we actually were applying what was available. So in this presentation, I think there will be something, let's say, good for those who like to stick to the old, and excellent things for those who are looking for some new horizons. So this topic is on the new channels and new applications, and I also credit here my colleague Natasha Strelets-Mahovic, who has been the co-author with this presentation. She will be with you tomorrow on the EPSSG presentation. So this picture has been already shown. I will not stay here for long. This is the part of which is the heritage. This is the current Severi with the 12 different channels, and what will be the change when we move on to the FCI and the new channels. The new channels will be both on the visible range and also on the near infrared. And for us, 5 more channels means, or more than just the amount of channels, of course, increases. But if you look at the individual channels, one doesn't see that much of difference. So actually, I will be showing you towards the end of the presentation is then how do we combine the available new channels so that we will have new effective products for better monitoring of the atmosphere. So one word still more about the continuity. The good news for us old-timers is that the MSG channels will be also available in MTG. That means the good news, we can have all the products we have been using until now, and they will remain also, as well as the standard RGB images like air mass RGB and so on. They will not disappear, which is good for the continuity. innovation part is then something where we have a lot of improvements in various scales, in spatial resolution, as already Munir showed, and then the temporal resolution, spectral resolution. All these increments will make big improvements in the products that we will have available in the operations. And because Munir already walked through this slide before, I won't stay there longer. I will show you some examples of the individual channels and some of the products that will somehow highlight what we actually mean with these new channels. How can you actually see the difference? But first, something about the temporal resolution, how the enhanced temporal resolution will affect us during this decade, as we are moving from the MSG images that you see on the left-hand side, the full disk imager taking pictures every 15 minutes, and the rapid scan mode 5 minutes. 5 minutes is clearly better for convection monitoring, for example, and with the new MTG, then we move first to 10 minutes resolution, and with the rapid scanning method, we will then move to 2.5 minutes resolution. That significantly makes not only the images smoother, but you also start seeing some development that you may miss if you are using just the 15-minute imagery. In convection scale, the things do happen fairly rapidly. On the spatial resolution part, it is clear that getting better resolution and getting better spatial resolution also increases your chances to actually monitor small scale features, like for example, the nighttime fog, which is often quite small scale feature. This is an image of the Balkan Peninsula with a severe night microphysics RGB image. If you compare it with the upcoming resolution, you can see that comparing these two images, you start seeing much more details, which is what we want. For example, if we want to zoom into the area here between Serbia and Bosnia-Herzegovina, you see that currently the resolution gives you an idea that there are some larger areas of fog patches, but you don't have the idea of the smaller and narrow fog patches over the river valleys. This is something that will greatly improve the monitoring of such events. Another example of a fog is the current, this is example by Martin Setvak over the Czech Republic. You see the current resolution at these latitudes will give you a kind of a pixelated image of the fog, whereas with the future you can have much better understanding of the outlines of the fog area. The enhanced spatial resolution, of course, also naturally affects and makes it much more easy to monitor the convection and the convective cells. For example, in this case, you can compare the image at the bottom, which is the current resolution, compare it with the image on the top, showing you much more about the details on the cloud top. For example, the overshooting tops, you start seeing them much better in this resolution. Another example of a recent storm that was in Argentina. So this one is using the ABI instrument of the NOAA satellite series, and you see that both the time and the spatial resolution will give you fairly good overview of the development and the merging of the cloud and convective elements. The spatial resolution also can be seen in the fire products. The fire products particularly also will benefit from the better dynamic range of the new instrument. So there will be a better detection of the fires, comparing again the current and the future capabilities of detecting the fires. You start seeing much more fires with much, and they are even the small scale, especially the fire is particularly often a small scale feature, and this will be improved in the future. Also, one more image of the enhanced spatial resolution is you can compare the severe image of now in this case on the western part of France. You see and you get a kind of a vague idea of the cloud streets here over the land, but with a better resolution you start seeing where they actually and exactly are located. So in the cumulus scale or large cumulus scale, you start really seeing the differences fairly well. Of the new channels, I have just chosen here the 0.9, 1.3 and 2.2 because they were also mentioned earlier here in this discussion. And these channels will bring quite a lot of new innovation and possibilities for getting better overview of what's happening in the atmosphere. So I'm just walking you through quickly of some of the aspects. These are kind of new findings, so there's still a lot more research to be done, but just give an idea of, for example, 0.9 micrometer channel, which is quite good in detecting the atmospheric low level moisture. And this product here and the respective weather chart on the left show you the capability of this channel to differentiate the moist air from the dry lower tropospheric air. So we see two fronts here, one of the occluded front here over the France with a moisture band, not so much cloudiness, but there's some moisture that you can clearly detect with this channel. And then another one, convergence zone here over the British Isles and North Sea. This will of course yield and lead us to a possible application of new RGB products, which are still yet to be developed. But in combination of some combining certain channels together, you may have in the end some new RGB products for particularly mapping out the lower level moisture. For 1.3 micrometers, we spoke a bit about the stray light problem, and it seems that it's not that big problem now. The thin cirrus detection is the key and has been let's say the initial intent for this channel. And there also the aerosol detection has been mentioned as one potential candidate for this channel. I'm just showing you two examples of thin cirrus detection by Ivan Smiljanic, and then another one, aerosol detection by Martin Setvak. And so this is a scene from over the Mexico 2 years ago. In the visible channel, you don't see much but the fairly clear skies. If you then use the dust RGB, which is fairly good in locating upper level cirrus as well, you start seeing some kind of vague signs of upper level clouds here and there if you compare these two. But when you use the 1.3 and you start enhancing it and playing with the thresholding, you start seeing much more cirrus over the area. And that's something we can clearly see that there's a use for this also in the climate applications and cloud masks and so on. And this one has been found out that it's fairly useful for that. For aerosol example, I'm showing you the one from last September. This was an episode of the widespread aerosols in the atmosphere due to the forest fires in the Northern Hemisphere. And the one image here is now showing you first the visible range image with some kind of haziness in the atmosphere, but it's not very clear. Then if you use 1.3, without the enhancement, it looks very dark. But again, when you do the enhancement, you start seeing that there's a nice plume of aerosols here over the whole continent of Europe. And finally, 2.2 micrometers cloud particle size. 2.2 somehow complements the 1.6. They both are very important for cloud particle size and cloud particle phase, and they should probably not be used alone. The best way, and I will show you an example next, is that they together, being used together, they will give you the best idea of the actual cloud particle and cloud phase structures. So the image here is now at the bottom, you see the 2.2 micrometers, and on the top you see 1.6. There's a slight difference. Ice clouds are rather dark in both, but with the different capabilities and a bit different spectral behavior, we can use them for preparing better RGB images, also for the cloud phase, and I will show you examples of that next. Many of these new channels now that we went through here, they will be mostly used as a part of the new RGB products. There's probably not much use for going through the individual channels as we can understand that. The 4 products that I have taken here are the ones that have already been used by our collaborators in USA and Japan and elsewhere. So the True Color RGB which uses the green channel, which will be the new one. Cloud Phase RGB that will exploit the 2.2 micrometer information, and then Cloud Type RGB 1.3 micrometers, and finally Fire RGB for fire monitoring. This one animation here shows the Japanese example of using the new True Color RGB, which will be in many ways better than the current day natural color RGB. It gives you a better, more natural overview of the atmospheric features. Another example here, this is taken from the EUMET train pages, is how you can interpret this new RGB in Europe. Cloud Phase RGB, as I said, it will be combining 2 different channels, and as a result, we will have a better differentiation of the ice phase and water phase clouds. This old example is of the northwest coast of Australia, so it's again Himawari product, and you have a fairly good differentiation of the ice crystal clouds and the water clouds, which are clearly in different colors. Cloud Type RGB uses the 1.3 channel, 1.3 micrometer channel, and again it's very good for differentiating different cloud types, high, cirrus, and low clouds, and it has been in use also in the USA already for some time. And finally, the Fire Temperature RGB is one of those upcoming products that we are looking forward to have, where you can have an idea of which kind of a fire it is, in which kind of a stage it is. Is it a hot spot, or is it less hot? And the different colors will indicate this for us. I warmly recommend you to go through the guidance on the EUMETSAT website, where also the new RGBs are all presented, and they will give you an idea of what's coming up. I might say that as a summary that the MDG will, as I said, it will bring a lot of innovation, as well as it will preserve what we already have. And the improvements that we will have will take place in various scales, in spatial, temporal, spectral, and dynamical resolution will be improved. And my final bullet here will say that as we see ever increasing number of RGB products, we already have quite a few, and quite a few standard ones and quite a few non-standard ones used maybe regionally or even in one country. With the new channels, we'll have again an availability of more and more RGB products, and in our opinion, this clearly requires international coordination. I think the coordination until now has been fairly well. We have seen how the certain products have been taken into use in various parts of the world. If we think, for example, Dust RGB or Airmas RGB, they are quite well known in different parts of the world, and I guess and I hope that this will be also continuing in the future. So they will be needing some international coordination. And I think I was trying to be fairly quick. Stefan, back to you.
Thank you very much, Vesa. This was perfect. Very good examples for the expected utility of the new channels in applications. The RGBs have been a resounding success story around the globe in weather forecasting offices. and the discussions around the next generation RGBs have started already. We're looking at expert workshops and community expressions of need in the near future as we move along and learn how to use FCI data once it becomes available in sometime in 2023, we hope. Okay, thanks very much to all the presenters for being with us today, and I take time for a few more questions to be answered live before we close. And as I said at the beginning, we'll make the recordings, the presentations available to all participants and publicly, and also the questions and answers in writing to you, so you will not miss anything. So let's go to some of the questions. So these are, I just go through them now in the sequence that they appear here. So these are for anyone who was speaking. So Munir, you're still with us, I hope. And I guess the first question is one for you. How long will be the period of parallel operations of Severi and FCI?
Okay. According to our timeline, end of 2023, we have MTG operational, and end of 2025, we decommission MSG. So that would be 2 years.
Yes, that applies to the 0-degree longitude service, correct? So Severi will be in the world for a bit longer, probably over the Indian Ocean on the best effort basis.
Mm-hmm.
Okay, this one is on the technical data reception side. What is the minimal technical requirement for MTG data reception, processing, and transferring? This is a difficult question because it really depends on exactly which data you wish to receive. If we're talking about the real-time data reception using EUMETSAT Europe, for example, you will need to upgrade your reception antenna, and you need at least a dual feed to receive data from both the restorable and the non-restorable service. And then there are certain requirements for the processing workstations that you need behind it and the software that is installed on them. So there is an evolution of the current EUMETSAT Europe receiving stations, which is documented on our website. So we'll make that available to you. But I should also add that, of course, the data volumes are increasing dramatically. So we're looking at a factor of 30 at least compared to current Severi data rates if we take all the data that we expect from MTG. So not just FCI, but also the IRS and LI emissions. We've had that question. That one. This one is interesting also for you, I think, Munir. Was the additional LI payload the only reason for MTGI to be 3-axis stabilized rather than a spinning satellite?
Okay, so of course for the LI, it would not have worked on a spinning satellite because you need to stare and detect small subtle changes. But of course, that's not the only reason. If you think, for instance, Himawari, they don't have a LI, but they also have a steering 3-axis stabilized platform. So the idea of steering is that you can spend the whole time looking at the Earth. Severi, because it's rotating, it's only spending, I think, a sixth of the time looking at a useful pixel on the Earth. The rest is looking at deep space. And as a result of that, to acquire your disk in 10 or 15 minutes, then you need to go over your pixel really fast. And the faster you do your acquisition, the less photons you acquire for each of your measurements, and the more noise. So to improve the performances, then we could only go with a 3-axis stabilized platform.
This one, can you tell us the improvements on the CO2 channel in MTG comparison with MSG? Thank you in advance.
Right. So in terms of noise, I was looking into it. I believe the radiometric noise content of the FCI is twice as low as the one on Severi, despite having smaller pixels of 2 kilometers instead of 3. And for the calibration accuracy, we also much better. I think for Severi, we are around 0.7K, the calibration accuracy for the CO2 channel, whereas for FCI, we are about half this this value. It depends where on the dynamic range, but we're also twice as better on the calibration accuracy.
Thank you. Yeah, I should remind you of the poll that we'd like you to respond to. It's a quick feedback poll on Slido on your impressions of this session today. Thank you. This question, how fixed is the launch date? It's always an interesting one.
So as you know, the launch date has been drifting significantly in the last 5 years. On this one, of course, we're getting closer to it, so you have an increased confidence. We have the ground segment, we have the satellite being delivered, and the most important thing is we want to launch on Sentinel, excuse me, Ariane 5, and that would be the last launch for Ariane 5. So it has to be launched end of next year, or else we would have to transition into a launch on Ariane 6, which will incur a lot of costs to launch it on a new platform, on a new launcher. And we don't want to be the first satellite to be launched with Ariane 6 also. So it would probably, if we don't launch end of next year, it would delay by many months. So we are pretty confident that it would be around end of next year, within a few weeks.
Yeah, so the move of the launch service provider Arianespace from their current model Ariane 5 to Ariane 6 forces us to get ready, and ESA and industry.
Indeed.
Okay. The top one here, Rayleigh correction of the visible channels gives a much better looking true color RGB. Will this be included in the true color RGB recipe?
Maybe I can say that we know that, for example, in USA, the Rayleigh correction has been applied into the green channel because of its much better quality. And I guess that that's already kind of building up the standard for that. It has to be also included in the true color RGB recipe here. But I don't have the details more than of that more at the moment.
Slide 10, that's probably Munir's presentation. Will the I1 satellite have, will the FCI on the I1 satellite have 4 enhanced channels?
Yes. Even in the full disk mode, we do acquire also the 4 high resolution channels. They are acquired, downlinked, processed, archived, and they will be also disseminated via EUMETSAT terrestrial. You should refer to the presentation by Katja.
Yeah, indeed, they will be disseminated to users either through EUMETCAST satellite or EUMETCAST terrestrial. Is it possible using the FCI level 1C test data to generate the natural RGB image as it's shown in the example RGB image of FCI generated from MODIS data?
Of course, you can generate your RGBs with the test data. It's made for that. It will not look like a MODIS image because what's in there essentially is are severe measurements resampled on an FCI grid. So it would look very much like the Severi. It has also the new channels for some of the data sets. It depends. We have released long time series ones where the new channels were simple replications of the nearest heritage channel. But we have also released a single repeat cycle with all the channels, including the new ones which were simulated. So you can try and see what it looks like. It would look like a natural RGB, but of a lower resolution than FCI because again it's Severi underneath.
That's good to know. This one is about technical requirements to receive MTG data. I think we had a similar question before. We'll provide an answer to that. This one is about the sampling. Does FCI oversample for east-west, north-south directions in orbit? Are the onboard sampling sizes the same as level 1C spatial sampling distances?
Yeah, so
sample 2 kilometers for water wave channels.
Some sensors perform oversampling in orbit and even spatial filtering before downlinking the data. It's not the case for FCI. The resolution we acquire in orbit is the same as the one we provide the L1C data on. So there is no really an oversampling or onboard processing. There's nothing that changes what the data looks like. For the channels at 1 kilometer and 2 kilometers, to be precise, they are clocking at 500 meter equivalent. So all the channels acquire a pixel every 500 meters, but then they are just simply averaged. So it's not really, I wouldn't call it oversampling and onboard processing. It has no impact on the image.
Okay, thank you, Monia. We've had this one covered. This one by Leon. Does redundant detector selection have any impact on geolocation or band-to-band?
They have a very tiny impact on actual geolocation or the actual pointing of a given pixel because there is a very small shift of possibly up to 10 kilometers, but it's a shift that we know very well of, and we know how our detector is made, and we know the position of all the pixels. So it has no really an impact on the product because then all of these are corrected. We shift back the pixel by the same number of columns so that it looks like an image. And in terms of performance of pointing knowledge, it has no impact because again we know the detector mapping very well, and it's very well controlled with very good tolerances. So changing pixels will not affect geolocation performance or band-to-band. Because then we rectify on a fixed grid, so it doesn't matter which pixel was activated. We know very well where acquisition came from, and then we are able to reconstruct almost a perfect image from it.
Okay, we're slowly coming to the end. I suggest we take this one for you, Monia, because this is about the modulation transfer function. It sounds as though you will adjust the MTF. Do you know how much this will be extended? This will extend the spatial error correlation, which is very important for NWP data assimilation. Is this procedure publicly documented?
So is it publicly documented? I think no. We will say a few words about it in the product user guide. The point is, through this process, we ensure that all the channels have the same MTF, so the modulation transfer function. So we actually control our data so that it's consistent. So I would think that for NWP data assimilation, it's a good thing to do. So all our channels have the same MTF at level 1C after the filtering.
Yeah, it will be good to include in the product user guide as many details as we can publish on this.
Yes.
All right. I think we should close the session for today. Thank you very much for your time. We will answer the remaining questions offline. And I want to thank all the speakers again for preparing presentations and for participants in joining us for more than 2.5 hours. So I think we've covered the whole range of the FCI world today, and we'll do the same for MTG tomorrow. So I think with that, I can close this session, and thank you very much, and wish you a nice rest of the day, a nice evening. Bye-bye. Thank you very much.
Thank you.